The Square Kilometre Array will be the world's largest radio telescope when it's built in about 5 years' time in southern Africa and in Australasia. And it's going to consist of radio antennas spread over distances of thousands of kilometres across the desert in those two locations with two different receiver types working in different frequency bands. So high frequency receivers in South Africa working at sort of mobile phone frequencies and low frequency receivers in Australia.
And, well, what actually is a radio telescope as opposed to an optical telescope, which we perhaps might be more familiar with?
Well, what we're really interested in doing with the SKA is looking at the very distant universe. We're looking here at galaxies where the light has taken billions of years to reach us, and because of that, we're seeing the universe as it was in the past. Now, we really want to see how galaxies are forming in the past. And optical telescopes can show us the light from stars, which are hot, but we want to see what that material was like before it formed into stars, before it became hot. And the wonderful thing about radio waves is that hydrogen actually produces emission of its own accord at a wavelength of 21 centimetres, that's a frequency of 1.4 gigahertz. And we can see that emission from that gas before it even formed into stars and see how it's forming into structures in the very distant universe.
And so that we simply couldn't see that with visible light. It's because it's radio waves that we need to use a radio telescope.
That's right. There's another very large project which will be built a little bit after the SKA called the European Extremely Large Telescope. And that is looking to detect the visible light from the first stars that form in the universe about 13 billion years ago. But the SKA is able to look at the gas before it even formed into those stars and see how it's forming those structures.
Why does the Square Kilometre Array need to be so huge, covering thousands of kilometres?
The fundamental problem is that radio waves have very long wavelengths. Now, to build an optical telescope to see the sky quite well, you need something like 10 metres or so across for your dish. But that's for waves with a wavelength of a few hundred nanometres. Now, radio waves have wavelengths of centimetres or metres, so about 1 million times the wavelength of visible light. And that means your receivers have to be correspondingly bigger. And if you multiply 10 metres by a factor of 1 million, you get up to about 1,000 kilometres, which is the size you need for the SKA.
And what are we hoping that it's going to do? I mean, you said it's going to look back to the very early formation of galaxies. How will it help us to understand that?
Well, first of all, the Square Kilometre Array is an observatory which will work on a very large number of projects. So what I talked about so far is actually just one of the more significant projects it will work on. It will also look at pulsars, which are neutron stars which are spinning very rapidly. And it so happens that because they're so massive and they're spinning so fast, they're very good clocks. And so they're as good as the best atomic clocks we have on Earth. And by looking at those clocks distributed through the Milky Way galaxy, we might be able to detect, for example, gravitational waves travelling through the Milky Way galaxy, causing slight changes in the distances to those pulsars. If you see pulsars doing that, you think, well, maybe there's a gravitational wave which is rippling through space, causing those pulsars to change in their distances from us. And pulsars will also be very useful for testing how gravity behaves in very strong field environments. So, for example, close to a black hole, does gravity behave as Einstein's theory of general relativity predicts? That's an interesting question, and we've never been able to put that to the test up until now.
What are some of the challenges that we face looking so far back towards the beginning of the universe?
The biggest challenge is that the light from these objects is incredibly faint because it's travelled so far. And that's actually why the Square Kilometre Array is called the Square Kilometre Array. If you add up the collecting area of all of the antennas, you get around about a square kilometre, 10 to the 6 square metres. In fact, you get about 3 times 10 to the 6 square metres. And you need to collect all of that light from the sky in order to see these objects at these incredible distances.
The array in South Africa is going to be picking up the high frequency, so kind of mobile phone kind of level. How do we stop it from being interfered with, you know, people's mobile phones and communication satellites, that kind of thing?
That's very true. The reason for picking these two sites is that they are very sparsely populated. You don't want people living close to a radio telescope because they will have mobile phones, they will have devices with Wi-Fi, Bluetooth, etc. And all of that generates interference, which you don't want in your signal. Now, the Australian outback is a wonderful site because it's completely dry and nobody lives there. Really, literally nobody lives there. You can take a square on a world map and you'll find half a dozen people live in that square on that map. So from the Australasian site, the principal source of noise are from satellites and aircraft flying overhead, and then you can try to track that out by knowing that it's a point source in the sky where the plane is. The Southern African site at the moment is still very good, though Southern Africa is a developing region and the population is growing, and that's one of the reasons why it's important to build a radio observatory there now, because it means we can preserve this very pristine environment for radio astronomy, and we can stop people from building radio and television transmitters in this very nice environment for radio astronomy.
And you said that they were going to be hopefully finishing in the next 5 years or so, I think. And when are we hoping to get the first results?
So construction will begin around 2017, 2018. It will then be a phased construction process. So I think the first radio waves will start to be detected around 2019. There will then be obviously a commissioning phase where you have to make sure the telescope is behaving as it should. We might expect some early science in the early 2020s. And then there's phased deployment of more receivers in what we call phase 2. And then by 2025 or so, the telescope will be operating at full potential.